So if you are, or maybe if you were, a network administrator, you definitely know that feeling. That specific kind of anxiety configuring a big network manually.
Yeah.
You've got this great high-level design, VLANs mapped out, routing protocols all planned, but then comes the reality.
Reality being logging into maybe hundreds of devices, routers, switches, firewalls.
And translating that genius plan into, well, just repetitive vendor-specific command line stuff.
Yeah.
CLI commands, over and over.
And it wasn't just boring, it was risky, like really high risk. Every single command you typed was a potential mistake waiting to happen.
Right.
The admin was basically a human compiler,
Yeah.
turning these abstract ideas into very, very specific syntax for each box.
And if you mess up one subnet mask or misconfiguring one interface,
The network doesn't complain loudly, it just
Yeah.
stops working, silently fails, and then you're
Yeah.
stuck troubleshooting for who knows how long, days, maybe.
that exact problem, that's what we're diving into today. This deep dive is all about the protocols, the architectures that finally started to fix this mess that enable real high-level network automation. So our mission is to really get under the hood of NetCon and its language, Yang.
The configuration side of things.
Exactly. And then we'll shift gears to look at OpenFlow and the whole idea of software-defined networking, SDN.
But to really appreciate where we are now, we kind of need to remember how bad it was. Why the old ways, like just using CLI, failed us.
Okay, so what were the big drawbacks?
Well, the main one was vendor lock-in, right?
Mhm.
Cisco iOS commands look nothing like Juno's command.
Yeah.
Or Fortinet, you had to learn completely different languages.
Even within the same vendor.
Absolutely. New hardware generations often meant new or changed commands, so you were constantly learning new dictionaries just to manage the gear you already had.
And that silent error thing you mentioned earlier, that sounds like the real killer.
It really was. You tell a switch, okay, enable OSPF in Area 51. You type it perfectly. The syntax is correct. The switch says, okay, done. But it can't check the logic. It doesn't know if Area 51 actually connects properly to Area 0 in your design. The command is valid syntactically, but it breaks your network logically.
And you only find out when traffic mysteriously stops flowing, followed by painful debugging.
Exactly. It's just not a solid foundation for automation where you need reliability.
Okay, so CLI was error-prone and vendor-specific. What about SNMP? We still use it a lot for monitoring, right? Why couldn't it handle configuration properly?
Yeah, SNMP is great for monitoring, for checking status, but it was never really designed for heavy-duty configuration changes.
What could it do?
Think small things, like maybe turning a port on or off, basic toggles. But the big issue is it uses UDP.
Ah, unreliable transport.
Right, so the network manager, the controller, sends a command and has no built-in way to know for sure if the device even received it, let alone applied it.
You'd have to send another command, like a read request, just to check.
Exactly. Send one UDP packet to change something, then send another UDP packet to ask, did it change?
Mm-hmm.
That just doesn't scale when you're trying to configure thousands of devices quickly and ideally all at the same time.
Okay, so that sets the stage. We needed something better. The goal then is to get the human out of that repetitive translation loop.
Precisely.
We want to define our network intent once and let some system, some server or controller, handle translating that into all the specific device commands.
And that whole shift really starts with getting the structure right, which brings us to netconf and the language it uses, Yang.
Yang, yet another next generation, quite a name.
Yeah, but it's the key ingredient. Think of it like this. Traditional CLI config is like giving a technician handwritten notes. Every vendor writes their notes differently.
Okay.
Yang replaces those messy notes with a standard, universally understood blueprint, a structured data model.
So Yang defines the structure for configuration data, making it vendor neutral.
Exactly. It's a common data modeling language. It forces configuration into a strict hierarchy, using standard building blocks, like a whole configuration section, say for BGP, is defined inside a container.
Okay,
A single setting within that, like an IP address or an autonomous system number, that's a leaf.
makes sense.
And if you need a list of things like multiple DNS servers or maybe a set of firewall rules, you use a list node.
Oh,
This formal structure just eliminates the ambiguity you get with free-form CLI commands.
and that structure, it's written so humans can read it, but how does it actually get sent across the network?
Right, so once the admin or the controller defines the configuration using this Yang model, it gets encoded. Serialized is the technical term, usually into XML that was the original standard, or increasingly common now, into JSON.
And those formats, XML or JSON, guarantee the structure for the machine reading it on the other end.
Precisely. No ambiguity.
Okay, so if Yang is the blueprint, the structured model, then NetConf, the network configuration protocol, is like the delivery truck.
That's a good way to put it. It's the vehicle and the protocol for how the client and server talk. NetConf uses what's called a remote procedure call model, RPC.
Like a client-server thing.
Yeah, very much so. The client, your network management station or controller, sends requests, which are the procedures, to the device, which acts as the server.
And security. We definitely need that.
Absolutely critical. Netcom is designed to run directly over SSH, so you get strong authentication, encryption, data integrity, all built in, running over reliable TCP.
Now, let's get to what I think is maybe the most game-changing feature of NetCon, especially for anyone who's had to coordinate network changes, the candidate data store.
Ah, yes. This solves a huge operational headache.
Explain the old problem first. If you needed to change, say, 20 settings across 10 different routers for a migration.
You were typically editing the running configuration directly, the
Yeah.
live config.
Which means changes take effect immediately on each device as you make them.
Right. Let's use that simple example of changing IP addresses on a link between router 1 and router 2. You logged into R1, you change its IP and maybe some routing settings. Bam! R1 is instantly running the new config.
But R2 is still in the old config.
Exactly. So the link drops instantly. Communication stops dead until you can quickly scramble over to R2, log in, and make the corresponding changes there.
Which basically forces you into scheduling a maintenance window, an outage, just to coordinate those few changes across two devices. Imagine doing that for 10 or 100.
Nightmare. So NetConf introduces the candidate data store. Think of it as a staging area, a scratch pad.
Okay.
The administrator or the controller can make all the intended changes across all 10 devices in our example, but applies them to this candidate configuration.
And crucially, these changes don't affect the live network yet.
Not at all. They're just staged. You can build up the entire set of changes, verify them, check them for consistency, maybe even run validation scripts against this candidate config.
And only when you're absolutely sure everything is correct.
Only then do you issue a single command, the commit operation.
And that one command does what?
It tells all the targeted devices to copy the entire configuration from their candidate data store into their running data store, atomically, simultaneously.
Wow, so the network transitions from the old state to the new state across all devices in one go.
In one atomic instant, yes. The potential outage window shrinks from minutes of frantic typing down to potentially milliseconds. That's huge.
That really is operating at the level of intent, not fiddling with individual device mechanisms under pressure.
Exactly. And NetCon also makes a useful distinction between configuration data, the settings you apply, like an IP address, which are relatively fixed, and state data, the operational stuff that changes all the time, like interface counters, link status, CPU load.
Different commands to get them.
Yep. You use getConfig to retrieve the configuration data stores, and a simpler get operation to just pull the current operational state data. Keeps things clean.
Okay, so NetConf and Yang give us structure, reliability, and that crucial simultaneous commit capability for configuring devices. But the intelligence, the control plane, largely still lives inside each device.
Correct. NetConf helps you manage those individual brains more effectively.
Let's completely shift gears now to OpenFlow. This sounds like a much more radical philosophical break. Software-defined networking, SDN.
It is radical. The core idea is centralization. If NetConf gave us a better way to talk to the device's brain, OpenFlow basically says, let's just take the brain out altogether.
Okay, so what's left in the device?
OpenFlow strips the network devices,
Yeah.
the switches, the routers, which in SDN terms we often call data paths, down to their bare essentials. They become really fast, hardware-focused packet forwarders, minimal intelligence on board.
So where does the intelligence go? The control plane?
It gets moved out completely onto an external centralized server called the SDN controller.
So the controller is like the network's operating system. It holds all the logic.
That's a great analogy. The high-level network policies, the applications that define behavior, they all run on the controller. And the controller uses the OpenFlow protocol, that's the southbound interface, to send instructions down to these now simplified switches.
Got it. And how does that communication work?
OpenFlow maintains a dedicated, persistent connection between the controller and each data path switch. It runs over TCP for reliability, and you can and should layer TLS on top for security.
Okay, so the controller tells the switches what to do. How does a switch actually handle packets based on those instructions? What's the mechanism?
The core mechanism inside an open flow switch is the flow table, or potentially multiple flow tables. These tables dictate every single forwarding decision the switch makes.
Flow tables. We need to unpack those. What's in a flow table entry?
Each entry, each flow, has a few key parts. First, there's the match field. This specifies the criteria the switch looks for in incoming packet headers. It can be really granular. Things like the input port the packet arrived on, the source MSC address, the destination IPv4 address, maybe even the TCP destination port. Lots of options.
And how does the matching work? If an entry specifies 3 criteria.
A packet has to match all the specified conditions in that entry. It's an AND operation. Every condition must be true for that entry to be considered a match.
Okay, what if a packet comes in and it matches the criteria for multiple entries in the table? Which rule wins?
Good question. That's handled by priority. Each flow entry has a numerical priority value. If a packet matches multiple entries, the switch executes the instructions from the entry with the highest priority number.
Ah, so that lets you create specific exceptions. A high priority rule to block certain traffic could override a lower priority rule that generally allows traffic.
Exactly. It's fundamental for implementing policies correctly. Then you have instructions what the switch should actually do if a packet matches. Forward it out to a specific port, modify the packet header, drop it, set it to another table.
And these rules don't live forever, right? You mentioned timeouts.
Correct. 2 main types. There's the idle timeout. If no packet matches this specific flow entry for, say, 60 seconds, the entry is automatically removed. Helps clean up unused rules.
Keeps the tables fresh.
Yep. And then there's the hard timeout. This removes the entry after a fixed amount of absolute time has passed, maybe 5 minutes, regardless of whether traffic is still matching it. Prevents stale rules from sticking around indefinitely.
You also mentioned multiple tables. How does that work?
Yeah, OpenFlow supports a pipeline of tables, starting with TableZone. When a packet matches an entry, one possible instruction is goTo table, which sends the packet to a subsequent table for further processing.
Subsequent meaning a higher table number.
Always forward. You can go from table 0 to table 1 or table 0 directly to table 5, but you can never go backward, like from table 5 back to table 1.
Why structure it like that?
It lets you break down complex tasks. Maybe table 0 handles all your security ACL checks. If a packet passes, it gets sent to table 1, which handles basic layer 2 switching. If it's IP traffic, maybe that gets sent from table 1 to table 10 for routing lookups. It creates a logical flow, like an assembly line for packet processing.
Okay, this is all making sense, but now we get to what you flagged as a really critical detail, something people often get wrong about OpenFlow. What happens if a packet enters a table and it doesn't match any of the entries currently programmed in that table?
Right. This is super important, especially for security. The default behavior if a packet hits a table and finds absolutely no matching entry is that the packet is dropped.
Dropped. Just discarded, not sent to the controller.
Correct. By default, it's dropped. It is not automatically forwarded up to the controller to ask, what should I do? That's a common misconception. The default is secure failure. Drop unknown traffic.
Wow, okay. So if you, as the application developer writing the controller logic, forget to program a rule for a certain type of traffic, the switch just throws it away silently.
Unless you explicitly tell it otherwise. If you want the switch to ask the controller when it encounters an unknown packet type, you need to program a specific entry for that.
Oh.
You add what's called a table miss entry. This is a flow entry where the match field is deliberately left empty, meaning it matches anything, and you give it the absolute lowest priority, usually 0.
So it only gets matched if nothing else, no higher priority rule, match the packet first.
Exactly. It's the ultimate fallback. And the instruction for this table miss entry is typically to forward the packet to a special reserved port called controller.
Ah, okay. So that's how the switch sends unknown packets up to the brain. You have to explicitly enable that path.
Precisely. The switch then wraps the packet inside a special OpenFlow message called packet_in and sends it up the control channel. The controller analyzes it, decides on the right action, and usually sends back a flow_d message telling the switch to install a new flow entry so future packets of the same type can be handled directly by the switch without asking again.
That closes the loop. Okay, speaking of the controller, what happens if that connection breaks, if the switch loses contact with its brain?
Critical failure scenario.
Yeah.
The switch has to revert to some predefined behavior. There are 2 main modes specified. First is fail secure mode.
What does that do?
The switch basically freezes its current state. It continues to use all the flow rules that the controller had already programmed into its tables. It processes packets according to those rules until they expire based on their timeouts. but it can't get any new rules or send any information, like packet in messages, up to the disconnected controller. It just runs on the last known good configuration.
Okay, running on stale data eventually. What's the other option?
The other is fail standalone mode. This is usually only an option for hybrid switches devices that know how to be both an OpenFlow switch and a traditional L2L3 switch.
And in this mode?
If the controller connection drops, the switch essentially gives up on OpenFlow. It ignores its flow tables and reverts back to behaving like a regular traditional switch, using its local MEC learning or maybe static routes until the controller comes back online.
Interesting choice there. Okay, before we wrap up and synthesize this, just a quick mention of a newer player in this space, building on some of these ideas, GNMI.
Right, GNMI, gRPC Network Management Interface. You can think of it as a modern alternative or maybe a complement to NetConn. It also uses Yang models to provide that structured data definition.
But it uses different plumbing.
Yeah, instead of NetConn's SSH-based RPC, GNMI uses gRPC, that's Google's RPC framework. It's known for being very efficient, often using something called protocol buffers for really fast data serialization.
What's the main advantage or focus of GNMI? Why develop another standard?
While it can do configuration, its real strength and focus area is on high-volume streaming telemetry, monitoring data.
How's it different from SNMP polling?
It flips the model. SNMP mostly uses polling. The manager has to constantly pull every device for its status updates. That creates a lot of overhead and doesn't scale well for real-time data from thousands of devices.
Okay.
GNMI heavily relies on a push-based subscription model. The monitoring system subscribes to specific data streams on the device, like CPU usage, interface counters, etc. Then whenever that data changes on the device pushes the update immediately to the subscriber.
Much more efficient for real-time data.
Vastly more efficient and scalable. It allows organizations to get much richer, near real-time visibility into network state across huge infrastructures without crushing the monitoring system or the network itself with polling traffic.
Okay, great overview. So let's try to put all these pieces together now. NetConn, Yang, OpenFlow, GNMI. What's the big picture takeaway for someone listening?
I think the core transition is clear. We started with manual, vendor-specific, error-prone typing directly into device. That was just unsustainable. NetConf and Yang came along to provide the essential structure and the reliable mechanisms, especially that candidate commit model, for configuring the static aspects of the network in a safe, automated, vendor-neutral way.
Setting up the device's brain properly.
Exactly. Then OpenFlow took a more radical step for the dynamic part, the actual packet flow. It centralizes the control plane, allowing you to manage the network's behavior, the traffic flow itself, from a single point using flow tables.
And GNMI enhances the visibility part with efficient streaming telemetry.
Correct. All these protocols, in different ways, are about moving the administrator away from low-level repetitive mechanism and towards high-level intent. You state what you want the network to achieve.
And these automated systems handle the how across all the devices, operating at the level of intent. That really is the goal, isn't it?
It is. It's the only way to manage the scale and complexity of modern networks effectively.
Okay, so let's leave our listeners with something to think about. A final provocative thought.
All right. We talked about those OpenFlow failure modes. Fail secure, where the switch keeps using old rules, and fail standalone, where it reverts to being a traditional switch.
Right, when the controller connection drops.
So here's the question for you, the network designer or operator. When your centralized automation fails, which scenario represents the greater risk to your specific network and your security posture? Is it worse for a switch to run blindly, potentially on outdated instructions, fail secure, or for it to suddenly become an unmanaged traditional device operating outside your SDN policies altogether? Fail standalone.
There's probably no single right answer. It depends on the environment.
Exactly. But the choice you make, how you configure that failure mode, reflects a fundamental decision about your network's security and stability philosophy when the automation brain goes offline. Something to definitely consider.